Okay, so what we were discussing last time, roots of, right? And in that we saw the statement of fundamental theorem of algebra. So what fundamental theorem of algebra says? Every non-constant polynomial with quotients, whatever quotients you take, real quotients or complex quotients, real or complex or integer or rational or irrational, whatever. So real or complex or integer, whatever quotients you take, has root, or all roots are in set of complex number. Right, so every non-constant polynomial always has a roots in complex numbers. Also, we saw the remainder theorem. So what is the remainder theorem? What is remainder theorem? So if f of x is a polynomial with real coefficients, right, and alpha is real number, right, then what is remainder theorem? If f of x is divided by gx is equal to x minus alpha, then the remainder is
F alpha.
f alpha. So you evaluate f at alpha, that it is a remainder. Also, we saw the factor theorem. What is factor theorem? So let f of x is a polynomial in Rx and alpha is a real number, then alpha, so x minus alpha is a factor of fx if and only if x minus alpha is a factor of fx if and only if f of alpha is equal to 0.
0.
Right, that is x minus alpha is a factor, x minus alpha is a factor of fx if and only if alpha is a root of fx. Right, so this is what we learned last time. So now we want to understand how many roots a polynomial of degree n can have, right? And we want to uh, see it is true in general कि every polynomial of degree n has at most n roots, right? Suppose f of x, okay, let f of x is a polynomial. So in Rx, so let f of x is in Rx. Let alpha 1, alpha 2, alpha m real numbers with alpha I not equal to alpha j if I not equal to j, ij from 1 to m. So all are distinct numbers such that f of alpha 1 is 0, f of alpha 2 is 0, f of alpha m is 0, right? Then gx is equal to x minus alpha 1, x minus alpha 2, x minus alpha m is a factor of fx. So what this theorem says, do you understand the statement? Is statement clear? What this statement says, that is, if alpha 1, alpha 2, alpha m are distinct roots, right, are distinct roots of fx, then x minus alpha 1, x minus alpha 2, x minus alpha n is a factor, right? So this is a factor of f of x means what? What we need to show? What we need to show? X minus alpha 1, x minus alpha 2, x minus alpha m, right, is a factor of fx means what? What is given? What is given? Alpha.
Roots are there.
So is a factor means given that alpha 1, alpha m are distinct real numbers, this is given. First thing. What is second thing? F of alpha 1 is 0, f of alpha 2 is 0, f of alpha m is 0. That is, alpha 1, alpha 2, alpha m are roots of fx. So this is given. What is our claim? What we want to prove? X minus alpha 1, x minus
X
alpha
minus alpha 2 is a factor.
is a factor of fx. Means what? That is, so this is a polynomial. What is the degree of this
Right.
polynomial? Right. So what is the degree of this polynomial gx, x minus alpha 1, x minus alpha 2 up to x minus alpha m? What is the degree? How many are these brackets?
M.
M
M.
bracket.
M.
Degree is m, right? So that is what we need to prove. F of x is equal to this factor x minus alpha 1, x minus alpha 2, x minus alpha m into some another factor, right, for some hx in Rx. So if you are able to express fx in this form, then we can certainly say that this is a factor because f of x is product of this factor with another factor. Correct. This is our claim. So how to prove this? So given that alpha 1 is a root of fx, right? Therefore, by which theorem? By which theorem? X minus alpha 1 is a factor, right? So by factor theorem, if alpha is a root, then x minus alpha is a factor. So by factor theorem, x minus alpha 1 is a factor, and therefore x minus alpha 1 is a factor. Therefore, f of x is equal to x minus alpha 1 into some p1x for some p1x in Rx, right? Because there is another factor which is p1x. Also, alpha 2 is a factor of fx, and alpha 2 is not equal to same as alpha 1 because the numbers are distinct that we are assuming. Therefore, f of alpha 2 is 0. F of alpha 2 is 0. That means alpha 2 minus alpha 1 into p1 alpha 2 is 0. Right? Because f of x is x minus alpha 1 into p1x. And alpha 2 is a factor means f of alpha 2 is a root means f of alpha 2 is 0. If alpha 2 is 0 means if we substitute x by replace x by alpha 2, then left hand side is 0, therefore right hand side is 0. Right? But alpha 2 minus alpha 1 is not 0. Why?
Alpha 1 is not equal to alpha 2.
Very good. And therefore p1 alpha 2 must be 0. But again by factor theorem, what happens? X
Alpha
minus
2 is a factor of P1 alpha,
ah,
P1x.
so x minus alpha 2 is a factor of p1x. Therefore, fx is equal to x minus alpha 1 into p1x, but p1x is now what? X minus alpha 1 into x minus alpha 2 into some p2x, right? Since p1x is equal to x minus alpha 2 into some another factor p2x, because x minus alpha 2 is a factor of p1x, right? Continue for alpha 3. Further, alpha 3 is a root of fx, right? Alpha 3 is a root of fx. Therefore, f of alpha 3 is 0. But what is the right hand side? Alpha 3 minus alpha 1, alpha 3 minus alpha 2, and into p2 of alpha 3, right? This must be 0 because f of alpha 3 is 0. But alpha 3 minus alpha 1 is not 0, and alpha 3 minus alpha 2 is also not 0, and therefore what is the only choice? P2 of alpha 3 must be 0. Correct? So that again by factor theorem, what will happen? Okay, is it correct? Whatever I have written is correct. Key x minus alpha 3 is a factor of p2x. Therefore, p2x is x minus alpha 3 into some another polynomial p3x. Right? Therefore, fx is equal to x minus alpha 1, x minus alpha 2, x minus alpha 3 into p3x. So, continuing in this way, what will happen? There exists a polynomial pmx in Rx such that what will happen? Same thing for alpha 4 and so on, such that f of x is equal to x minus alpha 1, x minus alpha 2 up to x minus alpha m into pmx. And what is the conclusion? What is the conclusion? What is the conclusion? Gx is equal to is a factor of fx. Right. So note here that degree of gx is m and m is less than or equal to degree of fx. Okay, so proof is clear now. Proof is clear.
Yes, sir.
So in this above expression, degree of gx is m because there are m factors, and which is less than or equal to degree of fx, and degree of pmx is less than or equal to, or it is strictly less, basically strictly less than degree of fx. So degree of factors is certainly less than degree of the polynomial fx. Right, so using this, so a polynomial fx, let fx is a polynomial in Rx if, so if degree of fx is fx is n, if degree of fx is n. What is n? N is a positive integer, right? Degree of fx is n, then what? Then
A
f,
is
fx has at most n distinct roots. Fx has at most n. If degree is n, then it has at most n distinct roots. If roots might be repeated, right? Then distinct roots may be, number of distinct roots is less. For example, so for example, if your polynomial f of x is equal to x minus 1 square, x minus 2 square, whatever is this polynomial, what is the degree of this polynomial? It is x raised to 4 plus something. You can multiply and see what is it. But what is the degree of this polynomial?
4.
4. But how many
4.
distinct roots?
2.
Right. How many
2.
distinct? So two distinct roots. And how many total roots? How many roots?
4.
4.
4.
But this, right. So roots are repeated. Roots 1 and 2 are repeated. So in that sense, how many distinct roots are possible? At most n, or a total number of roots, that is, so or equivalently, the number of roots, total number of roots is n. Total number of roots is n. So now, what is a proof? Suppose fx has, what is given? First of all, what is given? Degree of f of x is n. This is given, right? So given that degree of f of x is n, degree is n is suppose 5 or whatever number you say. So let so alpha 1, alpha 2, alpha 3, alpha m be roots of fx. Suppose alpha 1, alpha 2, alpha m be all roots of fx. Right. So if or roots of m, not necessarily all is not necessary, but suppose these are roots, then what is our claim? What is our claim? Ki how many roots are possible? What is our claim? At most n. And so what is our claim? Ki and how many are these alpha 1, alpha 2, alpha m? How many are these numbers?
M numbers.
M numbers.
Number.
And degree is n. And our claim is ki number of root cannot be more than degree. That means at most it has m roots. Right,
M
so
is less than or equal to N.
right, very good. M is less than or equal to n. So our claim is m is less than or equal to n. Fine. On the contrary, uh, assume that assume that ki m is greater than n. Right? Suppose number of roots is greater than, suppose it is greater than n. Let us see what is a contradiction. Right? So assume that m is greater than n. So let us see what contradiction we get. Right? So then by previous theorem, what will happen? We are assuming alpha 1, alpha 2, alpha m are roots, and the number of roots is greater than degree. Then by previous theorem, what will happen? X minus alpha 1, x minus alpha 2, x minus alpha m is a factor fx. Am I right? Is a factor of fx. Therefore, f of x is equal to what? G of x into some hx or some hx in rx. Is it clear? Whatever I have written is clear.
Yes, sir.
Now note that what is degree of gx? What is degree of gx?
M.
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 And degree of hx is greater equal 0. It may be 0 or greater equal 0, so doesn't matter. And therefore, what is degree of gx into hx is degree of what is it? Gx plus degree of hx, right? And degree of gx is m, and degree of hx is either 0 or greater than 0, right? So this is greater equal m plus 0. So degree of gx into hx is greater than or equal to m. Fine. So therefore, but fx is equal to gx into hx. Therefore degree of fx, which is n, degree of fx, which is n, is same as degree of gx into hx, which is greater than or equal to m. And therefore, what we found, n is greater than or equal to m. What happens? Contradiction. Why? Why contradiction?
Because we assume that M is greater than N.
Right, correct. We assume that m is greater than n. And what we found, n is greater equal n. So to the assumption that m is greater than n. This was our assumption, but what we found, n is greater or equal. And hence, what is the conclusion? Hence, if you assume that the number of roots is greater than degree, then there is a contradiction, not possible. Hence, m is less than or equal to n. That means the number of roots of a polynomial of degree n is less equal n. So polynomial cannot have roots more than degree. Right. Now, one of the important property of roots, if root is a complex number. So for example, if you look at f of x equal to x square plus x plus 1. So what are the roots? Do you understand what are the roots of this polynomial? What are the roots? Minus 1 plus root 3 by 2 times I. Is it correct? Is it true? What are the roots of this polynomial? Yes. X is equal to minus b plus minus b square minus 4ac divided by 2a. What is a here? 1, b is 1, c is 1. So what are the roots? Okay, is it correct whatever I have written?
Yes, sir.
Right, so these are the roots.
Yes, sir.
Now, what is the relation between alpha 1 and alpha 2? So these are complex roots. Alpha 1, alpha 2, complex numbers, not real numbers.
Conjugate pairs.
Right? And therefore alpha 1 is alpha 2 conjugate, complex conjugate. They are conjugates of each other, or alpha 2 is alpha 1 conjugate. And you know how to find conjugate. If z is a complex number x plus iy, then z conjugate is x minus iy.
Complex.
Right? So roots are complex, and then one root is conjugate of first root. Right? So, and therefore, is it possible that there is a polynomial with real coefficient? So my question is, does there exist a polynomial which has the roots 1 minus 2i and 1 plus I only? Does there exist a polynomial with real coefficients? There exists a polynomial with real coefficients. So what I expect here, polynomial with real coefficients whose roots are these only. It has only two roots and coefficients are real. Is it possible? What is your answer? Suppose alpha 1 is equal to 1 minus 2i and alpha 2 is equal to 1 plus I are roots. Then what is a polynomial? X minus alpha 1 and x minus alpha 2. What are the roots of this polynomial?
Alpha 1 and alpha.
Alpha 1 n, because f of alpha 1 is 0 and f of alpha 2 is also 0. So alpha 1 and alpha 2 are roots. This is a polynomial. But if you calculate this polynomial x minus 1 plus 2i and x minus 1 minus I, and simplify x square plus something into x plus constant. So what are the coefficients here? Are they real? Are the coefficients real?
No.
Right? So coefficients are not real. What is my question? Does there exist a polynomial which has these two roots, only two roots, and coefficients are real? Is it possible?
No.
Not
No.
possible. This is not possible, right? So, and so what is a general statement? What is a general statement? Or you look at another example, ki f of x is equal to x square plus 1. Is it a polynomial with real coefficients? Yes. Is it polynomial with real coefficients?
Yes.
Yes.
And what are roots?
X plus 1, x minus 1.
What are the roots? What are the roots of this polynomial? X square is plus 1 is equal to 0. That means x square is equal to minus 1. That means x is equal to square root of minus 1 plus minus. But square root of minus 1 is not a real number. Square root of minus 1 is not real number. Why? Why square root of minus 1 is not a real number?
It is imaginary number.
No, but why it is imaginary? It is imaginary because it is not real. But why it is not real? What is the basic property of real numbers which is not satisfied by this number?
It's square.
Because we cannot represent it on real line number.
Why? What is the basic property of real numbers which is
Square
held?
is negative.
Right. So square of every non-zero real number is positive. This is a very fundamental property of real numbers which is not satisfied by this alpha. Right? Square of every non-zero real number. That means for all x belongs to R, if x is not equal to 0, then x square is positive. This you have already proved in calculus. Now if alpha is equal to root of minus 1, then what is alpha square? It is negative. Square of this number is negative, therefore alpha cannot be in the set of real numbers. We cannot put this number into real numbers, that's why it is imaginary number. Right? So if f of x is equal to x square plus 1, then what are the roots? Alpha 1 is equal to I and alpha 2 is equal to minus I. These are two roots. That means plus minus square root of minus 1. So, and is it true that alpha 2 is alpha 1 conjugate or alpha 1 is alpha 2 conjugate? Is it true?
Yes. Yes, sir.
Right. So here polynomial is with real coefficient, but roots are appearing in pairs, right? And therefore, what is a theorem? So let f of x be a polynomial with real coefficients. f of x be a polynomial with real coefficients if alpha is equal to a plus bi, where b not equal to 0 is a root of fx, then alpha conjugate is equal to a minus bi is also a root. Right? If a plus bi is root, then its conjugate must be root. And therefore, what was our previous example? Does there exist a polynomial which has only these two roots with real coefficients? What is the answer? If 1 minus 2i is a root, then its conjugate must be a root. Right? If 1 plus I is a root, then 1 minus I must be a root if you want coefficient to be real numbers. Right? Okay, so what is our claim? What is our claim? So let, given that f of x in Rx, real coefficients. So let alpha is equal to a plus bi and b is non-zero, root of fx. B is non-zero means our root is complex number. In case of real, the story is different. So alpha is a root of this. Therefore, f of alpha, that means f of a plus bi is 0. Correct? F of bi is 0. What is our claim? What is our claim? What is our claim? Yes, what is our claim?
Conjugate is also a root of f of x.
F of alpha conjugate, that means f of a minus is 0. This is our claim, final claim, right? Okay, let us how to achieve this. So consider another polynomial gx is equal to x minus alpha into x minus alpha conjugate. Let us consider this polynomial. What is it? Do you understand what is this polynomial? X minus a plus bi into x minus a minus bi. Multiply these two polynomials, what you get? X minus 2a times x. You check whether I am correct. A square plus b square. You check the calculations. Right? What are numbers a and b? A and b are real numbers. When I say alpha is equal to 2 plus 3i, then what are 2 and 3? 2 and 3 are real numbers, but this together is complex number. Right? So a and b are real numbers. Am I right? So gx is gx in Rx.
Yes.
Gx is in Rx. Fine. So now if we divide by division algorithm, if we divide fx by gx, so we get qx and rx. We get qx and rx in Rx such that by division algorithm fx is equal to gx into qx plus rx, where what is the condition on Rx? What should be the condition on Rx?
Rx equals to 0.
Or degree of Rx is strictly less than degree of Gx. Right, now there are two cases. Case 1, suppose Rx is 0. Suppose Rx is 0. Then what will happen? Fx is equal to gx into qx. But what is gx? What is gx now? So you tell me, what is gx? Minus alpha x minus alpha conjugate, correct? X minus alpha conjugate into qx. And therefore what is f of alpha conjugate? What is it? Yes,
0.
0. And so what is the conclusion in this case?
F of conjugate alpha is 0.
Root of fx. Right? That means alpha conjugate is a root of fx. This is first case if Rx is 0. If Rx is not 0, second case, if Rx is not 0, then what is the possibility? Right. If we divide fx by gx, then there is a quotient and there exists a remainder. Then there are two possibilities for remainder. Either remainder is 0, or if not 0, then what is the possibility?
Degree of Rx is less than degree of Gx.
Right. Degree of Rx is less than degree of gx. That means degree of Rx is less than 2 because degree of gx is 2. Correct? Therefore, what is a polynomial with degree less than 2? Therefore, Rx is equal to some, right? So, Rx is some px plus q, or not q. We should use some different notation. So, there is a confusion. So, degree of Rx is less than 2. So, Rx is some lambda plus mu x. Right, this is a Rx. It may be degree 0, it may be of degree 1, but in general, degree of Rx is less than 2 means it is 1 or 0 for some lambda and mu in R. Whatever I have written is clear. Therefore, into Qx plus Rx, lambda plus mu x. Am I right? By our assumption, alpha is equal to a plus bi is a root of fx. Is it true? Is it our assumption कि alpha is a root of fx? Is it true?
Yes.
So also by our assumption, alpha is a root of f of x. Also, what is g of x? X minus alpha conjugate. And therefore, can I say that g of alpha is also 0? Yes.
Yes, sir.
Yes.
Therefore, f of alpha is 0, but f of alpha is equal to g of alpha into q of alpha plus lambda times mu times alpha. Right, so whole thing is 0. What does it mean? But g of alpha is already 0. That means lambda plus mu alpha plus 0 into q alpha is 0. ultimately what we get further. So what does it mean? Lambda plus mu alpha is 0. That means lambda plus mu times alpha is a plus bi is 0. Let us simplify this, right? Lambda plus mu a is plus, let us simplify this complex number, plus what? Mu times b I is 0. So what is this now? Complex number. This is a complex number which is equal to 0. And when a complex number is 0, if its real part is 0 and its imaginary part is 0. So lambda plus mu a is 0 and mu b is equal to 0. But mu b is equal to 0 implies what? Mu is equal to 0 or b is equal to 0. But is mu 0 or is b 0? Is b 0? What is our basic assumption? Go back and see
No.
what is our basic assumption. We are assuming complex root.
Not equal to 0.
Not equal to 0.
B is not 0. B is not 0, but B is not 0, and therefore what is the only choice? Mu is equal to 0. And therefore lambda plus mu a is 0 implies lambda is 0 because mu is already 0. And therefore lambda is 0, mu is 0, and therefore what is Rx? Lambda plus mu x is 0. Correct? And therefore what is f of x is gx into qx. But what is gx? X minus alpha conjugate into qx. What is the final conclusion?
0.
F of alpha conjugate is 0, and therefore alpha conjugate a minus bi is also a root of fx. Right, so this is what we have proved for general situation. If a complex number is a root, definitely a conjugate is a root. Question. So if f of x is a polynomial of degree 3, then how many roots this polynomial can have? How many roots?
3.
3, right? Is it possible that all 3 roots of fx are complex?
No.
Right? Not possible. Why? If a complex number is a root, its conjugate is there. And if there is one more complex number, then its conjugate must be there. So therefore, what is a remark? The number of complex roots of a polynomial in f Rx is even. The meaning of statement is clear. The number of complex roots of a polynomial with real coefficient is even. How many complex roots a polynomial can have? How many complex roots a polynomial can have? Right? For example,
1.
suppose 1 plus I is a root and 1 minus I is a root, 1 plus 2I is a root and 2 plus 3I is a root are roots of fx. Then by previous theorem, then 1 minus I, 1 minus 2I and 2 minus 3I are also roots. Right? If 1 plus I is root, then its conjugate has to be there. 1 plus 2I is root, there its conjugate. So therefore, if 3 are complex numbers or roots, then their conjugates are there. That means only 3 roots are not possible. If you have 3 distinct complex number or roots, then there are 6 complex roots. Right? The number of complex roots is even. How many complex roots? Even number of complex roots. Right? Am I right?
Yes, sir.
If f of x is a polynomial of odd degree, right, it is a polynomial with real coefficients of odd degree, then what can we say about such polynomial? Is it possible that all of its roots are complex?
No.
If all roots are complex, then number of roots is even, and but all roots, the number of roots is n, but n is odd, so that is degree of fx is n and n is odd. Right? If it is odd degree polynomial, then it is not possible that all roots are complex. That means then fx has at least one real root. One real root means at least one root is a non-complex, right? At least one root is a real root, real number.
Sir,
Yes.
but fx can have less n roots.
Fx has n roots, no problem. But it is not possible that all roots are complex roots. Do you understand?
But sir, suppose the degree of fx is n and there are less than n roots of fx, and if n is odd, n less than n can be even.
Are these all roots? Look at this polynomial. What are the roots of this polynomial? What is degree? 3. What are the roots of this polynomial? And what are the roots?
1 minus 1 plus root 3i the whole divided by 2 minus 1 minus root 3i the whole divided by 2.
Correct? Omega and omega conjugate. So these two roots are complex, but third root has to be real, no choice. If third root is also complex, then its conjugate will be there by previous theorem, and therefore there are 4 roots, but then degree of polynomial will be 4, which is not possible.
Yes, I understood.
Right, this is the problem, right? You may have, suppose you have polynomial of degree 5. It is possible that you have 4 complex roots, but fifth root has to be real, no choice. Because if fifth root is also complex, then its conjugate should be there, but then degree will be 6.
But sir, what if there is no fifth root? What if there are only 4 roots and all 4 of them are complex? It's possible,
Yes,
right?
it is possible, no problem. Right. For example, if you look at the polynomial, I will construct polynomial by simple technique. X minus 1 plus I, x minus 1 minus I, x minus 2 plus 3I, and x minus 2 minus 3I. What is this polynomial? X square minus x square minus 2x plus 2. Am I right? You check this 1 square plus 1 square. This is one factor. What is another factor? X square minus 4x, and then 4 plus 9 is 13. Is it correct? You multiply this, you will get x raised to 4 and something. So degree 4 polynomial. Correct? So what are the roots? You just try to find the root, you will get all complex roots, and these are the roots. Alpha 1 is 1 plus I, alpha 2 is alpha 1 conjugate, alpha 3 is 2 plus 3I, and alpha 4 is alpha 3 conjugate. These are the roots. So it is possible that if degree is even, all roots are complex. But if degree is odd, then at least one root is real. You may have all roots real, that is not an issue. Right. So, what is a polynomial? Is a polynomial with rational coefficients or integer coefficients whose roots are whose root is alpha is equal to root 2 plus root 3. So root 2 plus root 3, it is not a rational number. Am I right? So root 2 plus root 3 is not a rational number. But what is a polynomial? What is a least degree polynomial? What is a least degree polynomial with rational coefficients whose root is alpha root 2 plus root 3? Question is clear? Question is clear? Okay, let me make simple question.
Yes, sir.
What is a polynomial? What is a least degree polynomial with rational coefficients whose root is root 2? What is a least degree polynomial with rational coefficients whose root is root 2? And what is answer?
Minus 2.
X square minus 2. There is no degree 1 polynomial. There is no degree 1 polynomial whose root is square root of 2 and coefficients are rational. Because if you write the polynomial x minus root 2, then alpha is equal to root 2, then g of alpha is 0. So alpha is a root of this polynomial. That means root 2, square root of 2 is a root of this polynomial, but this polynomial is not in Qx. Coefficients are not rational. We want polynomial with rational coefficients and its root is root, square root 2. And therefore the only choice is x square minus 2. Now similarly, I want polynomial for this. Polynomial satisfied by root 2 plus root 3 and coefficients are rational. Alpha is equal to root 2 plus root 3. Does there exist? What is your answer? Yes or no? First of all, does there exist? What is alpha square? What is alpha square?
Minus 2 root 6.
Right? Then
5 plus.
alpha square minus 5 is 2 root 6. And now square it. Square into 6, 24. And what is the square? Alpha raised to 4 minus 10 alpha square plus 25 is equal to 20. Alpha raised to 4 minus 10 alpha square plus 1 is equal to 0. And therefore, what is a polynomial? Are the coefficients rational? Are coefficients rational?
Yes.
Yes, sir.
Is alpha root of this polynomial? Is alpha root of this polynomial?
Yeah.
And so it is a degree 4 polynomial, and therefore here the 4 is the least degree. You cannot go below 4. So that polynomial has rational coefficients, and root 2 plus root 3 is a root of this polynomial. So 4 is the least degree. And what are the other roots? Alpha 1 is equal to root 2 plus root 3. What are other roots? Because this is a degree 4 polynomial, it has 4 roots. What are other roots?
So it will have at the most 4 roots. Now, is it compulsory that it will have definitely 4 roots?
If roots are repeated, then no, then you will get same roots. But are they repeated? You find out. If roots are distinct, then there are 4 distinct roots. If roots are not distinct, then roots are repeated. Is it true that roots are repeated? Yes. So these are the 4 roots. You check this. Yes. Is it clear?